All right, let's go ahead and close that.
I have an online final. That's it.
Okay. I asked you already, have any questions about the syllabus or the course? Have you all seen any news? Any computer architecture news? Anything?
I just think there's something.
It's pretty big, actually.
Deregulation of the.
Oh, the only thing I've seen is about the whole free internet thing.
Oh, that's free internet, but that's not so much with architecture. That's more of a policy thing. But I see what you mean.
They found a security flaw in all the processors, pretty much.
Since 95, all Intel chips since 95, they have found a huge security flaw in it. All Intel chips.
Intel chips?
All Intel chips since 1995
Right.
have a security flaw where a process can read another process's memory. Why would that be a bad thing?
It's not supposed to.
It's not supposed to.
That's why you just have AMD and you don't have to worry about it.
So if you got AMD, you're good then?
Right now, AMD is still evaluating it. There's two big flaws that came out. They have confirmed they are not vulnerable to Meltdown, from what I said, but they said they may be vulnerable to Spectre. They're still evaluating it.
You also had an issue with Mac. Yeah.
So this is a hardware thing, which means it's irrelevant of your operating system.
okay.
Completely irrelevant. It doesn't matter what your OS
Okay,
is.
'cause
It is a
Apple
hardware
came
issue.
out with a comment about it.
Yeah, 'cause
they're
it's-
having a major issue with this.
So here, I think this picture gives it the best. Why this is a problem? Let's say someone writes a program with hold on, let me tell you what's going on here. Down here is someone writing a program that takes advantage of Meltdown, and then someone else decides to log in, complete different user, and put in their password. Well, with Meltdown, it's literally reading the contents of that program up there and printing them out here. Ooh, that can't be good.
So are these new techniques or?
Yes, this came out, or this, I should say, was released a month ago or two ago. Yeah, it hasn't been around that, well, it has not been officially around for very long. I mean, obviously, the problem has existed since 95, but
As long as we've been alive.
yes. And this is a hardware issue. What is that?
That's longer than
So if it's a hardware issue, how would you fix this?
Redo the hardware?
Which would mean you'd have to
destroy your computer.
Yeah.
and get a new chip. Right. Well,
have to do that for every single computer since 1995.
right. So technically, that is what you'd have to do. So they're doing some crazy software. Yeah, they're doing some crazy software tricks in order to get around that, because
That'd be a
that
lot
would
of
be
money.
that's a lot of money.
And they would be responsible for it.
Well, Intel is responsible for it. AMD is not responsible for this Meltdown one.
No.
Meltdown's the one where you have two processes. This is a perfect example. One running right here, and it can read another process's memory. Because there's a security situation, and we'll learn about that. It's user and kernel, where a user program, aka any regular program, is going to have bounds, aka cannot read and write just anywhere. It can only read and write in certain locations. And that's usually enforced via the hardware. Meltdown breaks that or gets around that so that a program can't actually read from anywhere else in the computer.
If you have only one processor or one core, does that still work?
Yeah, it's on the one core. Because remember, we're in a multitasking operating systems or
Okay.
machines, so you can have multiple processes in memory at time, because you're just swapping from one process to another, and they're all been loaded into memory. This just takes advantage of the fact that you're down here running, and then as you swap back and forth between the two programs, that's why there was a delay between when you typed here and you came here, because the OS had to swap back to this program then read what's up there and printed it out. So yeah, Spectre does something similar, but it's, I'll just say for the sake of argument, it is way more complicated and harder to pull off. But Intel basically, they believe, Intel hasn't officially said everything since 95, but it's believed everything since 95 is vulnerable. AMD has said that they are not to Meltdown, but maybe to Spectre. ARM chips, ARM has confirmed that their Cortex A7s through A9s are vulnerable to this as well. But anything beforehand or not.
They changed their sourcing for their chip, for their components, around 1995.
Oh, Intel?
Yeah, are they thinking that maybe somebody actually put this in and just nobody discovered it, or?
This is pretty new, so we will have to see as it evolves what's going on. Because yeah, there's only right now the problem is you go and search, it's all news articles all the way down, right? It's hard to find the pure. There are the technical articles that you can read, and I have only briefly read them. I haven't delved into them yet. But yeah, maybe they did put something. Maybe someone didn't. Who knows? We'll find out. Hopefully we'll find out. All right. So from a security standpoint, hopefully you can tell this is pretty important. It's important to understand what's going on. Let's see. Were there any other big news coming out?
AI stuff.
AI stuff?
Do you hear about that AI that got citizenship?
Yeah.
Yeah.
Does it understand what that
Already
means?
apparently wants kids and it said she
Yeah.
wanted to kill the world, so that's fun.
But does it understand what that means? That's my only question.
I don't know.
Does the machine actually understand what that means?
I hope not.
I hope it doesn't understand that killing the world literally means killing people.
Kill its creators.
I don't have a great
Let's go iRobot.
opinion of AI.
Yeah.
All right.
Not my
Let's see, anything
not
else in
my
the
view.
news? Oh yeah, so AMD is not as vulnerable. I wonder whose stock is going to do well coming up. Also, this didn't happen recently, but maybe a year ago, AMD finally came out with a chip that is faster than Intel. Yeah. Yes. Boom. And it cost half as much. So yeah, and by the way,
New chips.
AMD is really our friend, even if you like Intel. AMD has been your friend because back in the 90s, when basically if you wanted an x86 chip, it was Intel, period. Your Pentium 2, if I recall correctly, the chip, just the chip, not the rest of the computer, the chip would be about $1,400 to $1,600. And that's in 95 money. So this is, AMD on the other hand finally came out and said, we'll do it for half the cost, we'll do it for half the cost, we'll do it for half the cost. So that's why your chips have gone down significantly in price. And your machines as well, because now you can get a computer for less than $1,600, and that's in 2018 bucks, not 95 bucks. All right. So good. The competition is still alive with AMD and Intel, which is correct. All right.
Competition is good.
Yep. Any other comments, questions? We doing well back there?
The AMD performance thing that you were saying, did you talk about the Ryzen chips?
Mm-hmm. The
recently
Ryzen
came
ones
out?
that came out.
I have a Ryzen 5 and it's really good.
Yeah, it's good. I believe Intel released one that's better in most cases, so
Yeah,
they're going back and forth. Well, no, it's great that they go back and forth. It really is.
That's
So
good for
AMD's
us.
going to be releasing a new chipset soon, so.
We just need to keep that going.
Yeah.
Keep that going.
Because I've got the Ryzen and it does better with the better memory you have.
Oh, okay.
And the more
Yeah,
memory you have.
it's-
So it's really nice.
Okay, cool.
And you can overclock it like crazy. So.
Do you have a liquid cooling on it?
Not yet.
Not yet. That is nice because
It
the
does-
sound goes down significantly. It is
Well,
so
it's not
quiet.
even that loud right now either.
Oh, it can go down more.
It does overclock very well because mine was 3,500 megahertz, but it easily 3,800 megahertz.
Oh, okay,
It's
great.
The same temperature.
Cool.
Sorry,
I mean, hot, warm, whatever. But yeah. Whatever.
Computer chip.
Thanks, Gabriel. Any other comments, questions? Cool. Okay. Architecture, we are going to have tons and tons of layers the whole way through. Just like layers of an onion, we're going to have tons and
It's
tons.
cold outside.
That's good. Thanks. Good call. So now we're coming from the software end of things. So in general, we're just going to give hardware one bubble. That is not true, but we're just going to give it one layer because we're software people. You know, if it can't be fixed in software, it's a hardware issue. Let them handle it. I guess unless it's Meltdown and Spectre, then apparently it's our problem. But anyways, most of the time we think of hardware as one layer. Usually above it we'll have the system software. This might be your kernel, and then any of your system libraries, which are used to basically interface between your application software, aka your C code or your Java code, and translate that into something that your hardware can produce. So the first point, or the first layer to understand, is that you have your applications which use another layer of software, your kernel and libraries, and those are responsible for translating it into hardware. Why do we go with this design? Especially in Java. Java is a great example. Why do we do this in Java? Why does Java do it this way? Because you have to have a JVM, which you can think of as a system software, in order to execute on your machine. Why do they have a JVM?
Control. Control.
Okay, some control. Yeah, so for security reasons, that's a good reason.
It's simpler.
It's simple. How does it make it simpler?
Well, it makes it easier on the user because I'm gonna like write everything in machine code. It's like, you know,
Yeah.
Right. So once you write it in Java, how many pieces of hardware does it run on? Well, not quite. No, it doesn't run directly off the hardware. Correct. But because you have this JVM, how many pieces of hardware does it run on? Most. Most. Any piece of hardware that someone's written a JVM for, your Java code will now work for. On the other hand, if you wrote your software for a specific piece of hardware, you know, an Intel chip, and all of a sudden you wanted to run it on something else, maybe AMD with a different operating system, is it going to run? No, not at all. You'd have to port it. But if you wrote it in Java, and then you had a JVM to go for x86, another JVM for ARM, or another JVM for Mac, another JVM, you know, for Windows, all those combinations, you just had to write Java once. I mean, your Java code once. So that's the big reason why we do all these layers.
Makes it easier on us.
Yep. Oh yeah, and hardware is usually processor, memory, and I/O controllers. Let's see, was that? So what's going on here? You write your C code. By the way, from a computer architecture standpoint, C is a very high-level language, extremely high level. Some people like to call it a low-level language, which always confuses me because they're used to Java and they think Java's higher, but that's just silliness. C is pretty high, and we're going to stick with that because we don't want to get any more complicated. We're going to go and stick with C because C takes your code, compiles it into the assembly. The assembly is then translated or assembled into your binary, which is what your computer finally executes. So high level is something we understand kind of English-like. Assembly is a textual representation of what the instructions are. You know, multiply $2, $4, maps to probably the first 32 bits that you see down there, so forth and so on. All right, processor has a data path where your data is flowing, you know, integers, floats, et cetera, Control, how do you actually manipulate that data path so it does what you want? You know, actually add, move the integer into the correct memory location. And then we'll talk about cache, which is a way to speed up memory. Okay. These, I wanted to give you at least a pictures of what a CPU looks like. Might be hard to see with this projector. But this is was an Apple A8. They're up to A9 right now, but that's actually might be A10. But what do you notice about this processor?
It has parts.
It has parts. Yep.
It's random.
it's very organized.
It's very organized. Might be
that, like,
really hard to
wasted
read from
space,
back
or
there.
there's,
Yeah,
like-
looking at the motherboard or whatever.
This is a processor. This is the Apple
really,
A8.
really small processor. That
Yeah, this is the tiny processor that does your work. You can kind of see it from back here. Not
Yes.
everything is labeled, probably because they don't release what everything is.
It has integrated graphics.
It has integrated graphics. That's a big thing that's happening nowadays.
It's kind of a pain.
So you have your CPU and then you have your GPU to the side. Very common.
It's 4 cores.
Cache on the CPU.
Has multiple cores. That's another big feature nowadays as well. L1, L2, L1, those are all memories, caches. SRAM, another piece of memory. DRAM interface and a DRAM interface, those are connections to your RAM as well, your memory.
Not at the bottom.
And he's got one at the bottom too. So a lot of memory connections.
Lots of memory.
So let's look at a different one. The 4th generation i7. Can you tell me about this one?
More color.
More colorful, nice. I'm sure when you open it up, it makes those colors. Yeah.
So
It's still
processor,
4 cores.
graphics is a GPU. It's got 4 cores. It's got a cache, and then it's got a couple memory.
All right, so this one is a shared L3. Back then you had L1, L2, which means each of these chips have L1, L2, which is probably the L2 is about this big and the L1 is just up here. So how much of this chip is actually consumed by the cache? A good amount, yeah, because also your processor is going to have cache in it as well. They don't label it. Cache is consuming a lot of your processors. In some processors, the majority of your chip is just cache. And that
That's annoying.
you'll see why that's the case. Basically, because memory is way too slow going on. And then at the end, you have your controllers over there. The controllers aren't too complicated, except for your memory controller, of course. But all your other ones are usually fairly simple. Okay. Also, what's that transistor count? 1.4 billion. It's a lot of transistors. Okay. Just want to give you an idea of what chips kind of look like nowadays. You have a lot of components, and they're integrating more and more on the chip. And why do they want to integrate more and more on the chip? That's the question. Why are we doing this?
To make the computer smaller.
Make computers smaller, yeah, so you can have smaller chips. That's a good one. There's another big reason.
You can have multiple chips.
Actually, there's multiple reasons for this. Smaller? Smaller is, there we go. You want it to be faster. Also, if you integrate it all on a chip, you also, in general, will consume less power if compared to trying to make them all separate. So there's a lot of reasons to go towards this. Does Moore's Law help you with this? Yes,
Smaller.
it does. Yeah, because if you can keep adding more and more transistors, you can make these cores tinier and fit more and more things on it.
Magic.
Magic.
Then you can
Magic.
have more cores. Just
You can
like
have more.
double
Why
the
not?
transistors.
Why not?
Yeah.
How many does Threadripper have? Is it 16?
I think so, yeah.
Yeah, 16,
It's
and then
not a
they,
lot. It's-
and then they have hyper threading, so it has 16 physical, 32 virtual. Yeah.
It's like $2,000? No, I think the first one starts out like that.
Yeah, the first one's not too.
What is hyper-threading? Is that a long explanation or a short explanation?
To really understand, it's a long one, but the idea is that you're going to run multiple threads on one core. You're going to try and run. You've done multi-threaded programming?
Okay.
No. So some programs can have multiple pieces of execution. You try and run both of them simultaneously.
What's the parallels?
It's parallelism, yes. While with a core, you have different full sets of execution. With a thread, you have very small sets, so hyper threading, which is really called symmetric multi-threading, which we will get to. Will try and run multiple threads on one core. As you can see, lots of little things. All right. We do need to keep in mind what's the difference between volatile and non-volatile memory. Volatile memory loses instructions when it's powered off. Where is that?
RAM.
RAM. Yep, your RAM. Also, any memory on your CPU is lost as well. So if you store something on the CPU, it's gone. Non-volatile is usually something separate. You have magnetic disks, spinning disks, flash memory. You have a lot of SSDs, and then your optical disks are also non-volatile as well. Maybe I should put Blu-ray up there. I think y'all got that. All right, networks. We're going to talk a little bit about networks, but not too much. Y'all know about LANs and WANs. Bluetooth is also a network, by the way. More of a personal area network.
The pan.
PAN. That's what it's called, a PAN, personal area network. All right, let me see if I can explain this picture. So, continues to evolve, increase capacity and performance, reduce cost. So, relative performance of your machine for $1, we say your performance is 1 with 1951 with your awesome vacuum tubes. I don't know if y'all have actually seen those, but they are. Hey, some people are all about them when it comes to sound. Like vacuum tube is the best. I'll let them have it. Transistor came out, and people were like, "Whoa, this is amazing!" And then they said, "Well, now we can integrate transistors because transistors were vacuum tubes. This giant thing. Transistor, you'll have it's actually a physical object. You kind of have to solder onto a board. Integrated circuit was a big jump because now you can have a piece of silicon and essentially etch into it. And then we're just they call it very large. Okay, we etched a lot of them, and then ultra large, we etched even more. Yeah, it's just going to keep on going.
The ultra,
Super mega ultra large.
ultra.
Yeah, I'm looking for the super
mega ultra.
special edition.
Yeah.
Special edition.
Special edition.
DLC not included.
Yes, and not nice. Okay.
Really fun here.
All right. So, cost per performance is going up. Looks like pretty much exponentially. Silicon is a semiconductor. Y'all have probably heard of that. Do y'all know what that means? Do you have any EE guys?
I kind of understand it.
So what is it? What were you taught?
It's like you can conduct kind of. It can be blocked or it can allow or not allow electricity.
All right, so
it's a semiconductor.
So semiconductor, right? That's a good one. For our class, the best way to think of it is that with a semiconductor, if you, depending on how you treat it, depending on what you add to it, you can make it a conductor or an insulator. For this class, just think of it that way. By the way, at the beginning, I'm going to do a lot of hand waving because we are not electronic engineers. Just telling you all that right now. That was the first one. Conductors allow the flow of electricity, insulators stop it, and then a switch, just like a light switch.
Switches in between.
No. A switch actually either allows the flow or doesn't allow the flow.
It's just like, nope, you're done.
Yep. All right, here's an extremely high-level view of how we create our integrated chips, aka the important parts of the processor. You get a silicon ingot, which is a giant cylinder of silicon. You go through a slicer and you make wafers out of it. So, yeah, that's what we call it, wafers.
Yum.
And this is we do 20 to 40 steps where we etch on the processor.
Song wax off.
This is me waving my hands. We etch the processor on the chip. It's a very, very complicated process.
It's magic.
It's magic. Right now, just think of it as magic. So then we have our chips on the wafers. We go through a tester, figure out which wafers are completely bad, throw them out. We dice them up
Waste
into
the
chips, into dies, and then we test them to see which ones are bad, throw them out. We try and put them on a package because your chip is not just a silicon, it's usually on top of something with a lot of little feet. Anyone who's built one, you know what I'm talking about. I'm assuming you built one yourself?
A computer?
Yeah.
Yeah.
Yeah, so you got the chip and it had a ton of little pegs at the bottom? Yeah.
Yeah.
So that's the package. It's inside the packaging, which is the feet and that plastic coating. Then they test the part. Again, throw out the bad ones, then ship it to customers.
So where does the silicon lottery come into play? Is that in the beginning step? When you make the wafer?
Okay.
Somewhere.
I better ask, what have you noticed about this process?
Lots of testing.
Lots of duds, lots of testing. Yeah,
I like to throw things out.
well, what if there's an impurity in the silicon up here?
Oh, you're screwed.
Right. Oh, we found it. Oh, we found it. Oh, it was over here. Yeah, huge problem making sure the silicon is as pure as possible, as well as making sure you did this step correctly, which, when I say waving hands, it is a magical process. This is a huge issue. For some processes, for especially high-end processors, the number they expect that 90% of the chips will be thrown away by the time they ship it out.
That's a big.
Yeah, for some of these things, it's really bad. Most of the time, it's probably around 10 to 20%, which is still pretty huge. But this is a big problem trying to make this as pure as possible because, I mean, your transistors.
Recycle the old stuff, I'm guessing, or?
I doubt it. I mean, you could throw it away, but that's someone else's problem. You know, a company makes this for you. The manufacturing gets the silicon ingot, and their job is go from the ingot to ship to customers. So you get this from another company, you might be able to give it back to them, and they might be able to purify it, remelt and whatnot, but it's not an easy process. All right. Yeah, it is.
I think sometimes they can, like, if it's like a 12-core processor and 8 of them don't work, they'll cut off 8 and ship it as a 4.
That's exactly what they do. That's exactly what they do. If y'all remember the PlayStation 3 with its huge cell processor they made a big deal out of, it actually has it has a PowerPC and then 8 cores, but it only guarantees that 7 of those 8 cores work because of this. Because by doing that, what's the word? The number of cores, number of chips they could ship was way higher. So they would take the performance loss, which is 1/8 performance loss right off the bat, no problem, just to allow it. Yeah. All right. Oh, so there's an i7 wafer. Look at all those chips.
Yeah.
Hey, what I always found funny about this is like, so definitely not. Oh, you got the tip burned off. You're not a chip because it's actually
Circle.
yeah, it's a circle, and you're actually making rectangular chips out of it.
So why not just
Why
make it
would
a
you just make it a
rectangle?
rectangle?
Yeah.
I'm all due to the way the process works.
Due to the wax on, wax off. No.
All right. Sorry, man. Hey, go get an E degree. I'll make way more sense. What?
I'll make it better.
You make it better. Oh,
Make it a
Your wafers-
rectangle.
Your wafers are made
Make it-
of silicon, right? I mean, so.
silicon with carefully added minerals and wires.
At that process there when you're etching.
Oh yeah.
So what I'm saying is that if your silicon is not exactly hard, it's not totally liquid, but it's easier to transfer through tubes and such. You might as well, the tubes are round, so that's probably why.
That's probably
Make
good.
it
The shape of the machinery involved.
Oh yeah.
You get the transfer.
It's always been diameters every time I look. 4-inch, 8-inch, 12-inch, 16-inch.
So what you're telling me is we need to make a rectangular tube
We need to make rectangular cylinders. Yes.
and then make a rectangular prism.
Wait.
Silicone.
Wait, hold on a second. What did I just say?
Change sides.
The whole like, I need you to draw 12 lines all perpendicular to each other. Like, wait, what? All right, we are going to be using Verilog in this course. Verilog, unfortunately, you will find the language has a lot of support, the tools not as much. Sorry, guys. This is something that's still,
What's it your for?
it's not really my fault. It's their fault. We're using Icarus Verilog, which is free open source, so we're going to stick with the open source one. If you want to buy it, it's usually a good $10,000.
Oh, hell no.
Okay, all right, good.
Oh, it's pocket
Glad
change.
we-
this.
Glad we had this discussion. Linux has, of course, package managers. If you're using Linux, just apt-get install Verilog, and it'll probably come right in. Windows, you're going to have to click here and do it.
When you do it on
Is
these
there no Mac
machines,
way?
Right?
They should have them.
Is there no Mac way?
I think that'll work in Mac.
That'll work in Mac.
But that's my guess. Can't hold me to it. You have to go look it up. Just look up Icarus Verilog space Mac.
Space Mac.
Space Mac. I know.
So is there a space between Icarus and Verilog?
Yes, there is.
I think you
Yes.
specified the space between Verilog
All right.
and Mac, so I had to.
Verilog is an industry standard. VHDL is also one. They're two competing
So
standards.
many of them.
It does work.
We will be building a simplified MIPS processor in this class. Why am I doing MIPS? It's simple and it showcases many of the modern architecture techniques. Why don't we do x86? Well, it's complicated, but actually very easy to do once you understand MIPS. My favorite quote's from AMD. It goes, "x86 is not hard, it just doesn't make any sense." The issue is, the thing about x86, well, let's see. Do I get another one? Nope, okay. They wrote it in 1970, and that was a kind of an 8-bit version, or maybe it was 4-bit, I can't remember. But all they've done since then is just keep adding instructions. So, and the reason for that is that any of your programs you wrote back in 1970 will still run on your modern processor. And backwards compatibility is king in computer architecture. Intel has tried to kill x86 on more than one occasion, and they have failed every time. The inventors of x86 have tried to kill x86, and they have failed.
The creature has become strong.
Yeah, the creature has become stronger than the creator. That's exactly what has happened. What'd you say, Alex?
Yeah, that's insane.
It is insane. Yeah,
Like they just can't figure out something better than that? Or
Oh, we got things way better than this. We can, if we redesign the architecture, all our chips would be faster and consume less power. I can virtually guarantee you that. The problem is backwards compatibility. The biggest thing that happened is when we're at 32 chips and we're going to go 64-bit. Intel was like, okay, we've had enough of this because it's been 8-bit, then they added 16-bit, then they added 24-bit instructions, then they added SSE, SSE2, SSE3. They added a bunch of crypto stuff, all blah, 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 all on top of the processor. Like, okay, we can design this way better. They came out with something called Itanium, which the compiler will help improve the performance of, and it'll consume less power. They released it. It then got the nickname of the Itanic because no one really cared about it. It didn't run Windows. It didn't really run too many Linux derivatives. It was expensive at the time because x86 has been around for so long. Everyone has the fabbing capabilities. So they were like, well, we still want x86 even though it's 32-bit, even though the Itanium's faster. So then AMD came in and said, oh, well, we'll release a 64-bit version for you. They released it, and of course Microsoft and everyone else was like, great, we're going to be using that. And then Intel was like, okay, fine. Then they created their 64-bit version as well. There's your quick history lesson. Yeah, they can't kill it. It won't die. Okay, and we'll actually go into a lot more specifics about that because when RISC came out, they thought it was going to die, but then it didn't.